So for me, just to clarify for myself, this is only if we're doing a random sample, because for me, what's going on in my head is I'm thinking if I have a large sample and we get something like 61%, and then that percentage is still high, I'm thinking back to significance.
And
I'm
it
thinking
could have
there
happened
has-
at random, then you won't reject the null hypothesis.
Okay.
This is where it's all going to piece together.
Okay.
Okay, so number one, we said
If someone previously knew it.
kind of the two reasons we talked about why somebody might choose the guy on the left, or what are those two things. We said number one, maybe they look like Tim, right? So and what did we call that hypothesis?
Facial prototype?
So I refer to this as facial prototypes. Just meaning that they have some idea of what a Tim should look like, and the guy on the left, or whoever, which one of them matched it better. And that's how they chose. And then the second reason we said people might be using, or the second method for choosing their face would be what? At random. Choosing just at random, right? No real reason behind it, just they chose. Like flipping a coin in their head, choose between two, they chose either left or right. So we can sort of think of this as like, either they were choosing at random, or they're not choosing at random, and something else is happening, right? And we decided to name this something else, like facial prototypes looks like somebody that's, if it's not random, it's probably this. So this is number one. And so today we're going to sort of, I want you to think about these like this is our null hypothesis. Nothing's happening, they're just choosing at random, there's no reason why. And this is really more of our alternative. If it's not happening at random, that means they have some reason. And like really our research hypothesis, being more specific, is we think that reason is because they look like this idea of Tim. Right, so number two, back to that thing. So I would say even you could jump over to number four and fill this one in. Right, if we think about our little faces experiment, what is our null hypothesis? Again, the null hypothesis is always the nothing happening hypothesis. So this would be people, they're not doing anything, they're just choosing at random. Right, this would be our null hypothesis. And then our research hypothesis would really be, they're choosing based on what they think a Tim looks like.
Why does it say, remember the research hypothesis differs from the alternative hypothesis? I thought research hypothesis and alternative hypothesis were the same.
So they can be used interchangeably, but like when you see research hypothesis more often, they're talking about a more specific version of the alternative.
Like what would need to be more
So like I could say it's either random or it's not random.
Oh, I see.
And that would really be the null the alternative would be it's not random.
Okay.
But really my research hypothesis is what I think is going on. What I think is going on is they have some sort of facial prototype.
So you're getting more in depth.
You're being
but
more
not
specific,
random.
yeah.
Okay. So if it's just asking for alternative hypothesis, it's okay to say it's not random?
Yeah.
Okay.
Because those two options always have to cover like the alternative and the null always have to cover all the possibilities.
So is the research hypothesis also abbreviated by HA stuff? Or is it by
It
HR?
can be, yeah. I mean, there's no like official abbreviation for it. Yeah. I would just say this is really what we're treating as sort of our alternative, but it's like our more specific alternative. So number two asks like, when we looked at our class samples, and we were, right, this is the whole point of that last one we just talked about. What did we end up thinking about facial prototypes? So we ended up getting with that result right about 11 to 12% chance of that happening. What do we think of that? So I'm jumping a little bit backwards to,
Classwork 13?
right, to classwork 13. We found that there was like 11 to 12% chance of getting our result, right? That number 11. Yeah. So what do you think this says about this? Do you think that it's, like, which do you think? Random or facial prototypes? Right, so going back to this thing, when we had 45, this was our result.
So this was our class you're talking about.
Mhm.
I remember there's a
And we said
40
60%, and then the chance of that happening
was 11.
was 11 to 12%.
That means it was 11 to 12% random.
11 to 12% likely that we would see this if people were choosing at random.
That's not.
So what do we think about the,
So that's for like 9% chance that it was facial prototypes, right?
sort of, right? So this is really telling us, is it this? Like, or what are the chances that it's this?
11 to 12%.
So people may differ. This is, again, it's sort of like that discrimination thing we did. People may differ in whether they think 11 to 12% is still pretty high, it could be random. And some people may think that's really low, I don't think it's random, I think it's the other thing,
So what's the
right?
whatever?
In this case, we don't beat the 5% rule, right, that we used before. If it's lower than 5%, that's enough to reject this. We're not there, right? It's still more than 5%. So like it could be people are choosing at random, but the number's still fairly low, right? So it's looking favorable to the prototypes, but maybe we're not entirely convinced yet by this. Right? Sort of. Because we're trying to figure out which one is it. Is it they're choosing based on he looks like Tim, or are they choosing at random? We said with our sample size, the chance of getting this result at random was about 11 to 12%. So it's not necessarily enough to rule this out, but it's still fairly low. So I would say maybe it's possible it's still happening at random, but this is maybe kind of a plausible explanation, right? We're not sure yet.
Can we just put 11% is not less than 5%, so therefore we cannot reject the null hypothesis?
Yeah, well, that's what we would have to decide here, right? So we can't reject this, in other words. But again, it's kind of, if we had 100 people and we had this result, then we'd be able to reject, right? But we didn't, we only had 45 people.
That's why you want a larger sample size, so you can get a more accurate.
Right. Mm-hmm. Right, so
that would be for number 2, right?
yeah. Let's take a moment to. So, right, how likely were we to get this particular result by chance alone or at random? If people were choosing at random, we were 11 to 12% likely. And again, depending on each person's sort of intuition, you may think that that's good enough. If we're sticking with the 5% rule that we generally use, we don't quite get there.
So if we were out in the real world and we were actually like doing this, like
Doing
an
research,
actual study,
You would not be able to reject your null hypothesis.
okay, we would have to follow the 5%.
Yeah. Right, because keep in mind, we do these statistics to try to answer a question about a research project, a research study, some other question. We don't just do the statistics because statistics is fun, right? Statistics is a tool to get us somewhere. And so in this case, it would be to answer this question, do people use spatial prototypes, or is that not really a thing and people are always just choosing at random?
Okay, so I have a question. So if you're like out in the real world and you're doing this as an actual study and your sample size is 45 and you get the 11 to 12%, but you do the exact same study with a sample size of 100 and It's like, how do you know which one to use? Because one, you reject the null, and one, you don't reject the null. But they're both the exact same study with the exact same things, but you just, your sample size is different. How do you know which one to use?
You would replicate it then, right? You would
Yeah,
keep
you
doing
would
it
want to replicate it.
and take the
Again and
mean.
again.
And yeah, and
Just stick with
generally, more people is going to be better.
So you just always want to use, you don't ever want to.
If you had the option, use 45 people, use 100 people, you'd want to use 100 people.
Oh, okay, always.
So we're gonna do very quick review, well, it's not gonna be that quick, not gonna lie. A review of some concepts, some that we probably know pretty well by now, and others that are like just starting to take form. So, samples and populations, which one's bigger?
Population.
We're all clear on that by this point? Okay, and so what's the difference between a population and a sample?
You take your sample from the population.
We're all good on that? Right, the population is everyone you care about. The sample is the people you really have the data from. Right, you pull your sample from the population. So we obtain our data measuring some variable or variables in a sample.
Is this stuff we're supposed to be writing in space for number 3?
If you want to do the review right there, you can. There's just space there, but we're gonna get to more complicated. That's why I say it. That's why I'm recording it, so you don't necessarily have to try to get everything down. So our sample is a subset taken from our population, and then we use that sample to make some sort of inference or conclusion about the bigger population. All right, so this is something we've been talking about since basically like the second day. So hopefully, also, as a kind of a caveat, you want your sample to be fairly representative of the population. If your population has males and females, but your sample only has females, you're not going to be able to draw very good conclusions about the whole group, right? Because it could be specific to just females. Right, so you want it to be fairly representative of the overall population so your results are not biased. Right, and this is more stuff you'll get into like research methods classes, but just something to sort of keep in the back of your brain. You want your sample to represent the overall population. So, example, if you have different types of cats or different types of people, you'd want them to be represented in roughly the same sort of proportions in your sample as in the bigger population. Why don't we just always collect data from a population?
That's really, really hard to get data from everybody.
It's at least really, really hard. Sometimes it's just plain impossible, right? Gathering data costs money, it takes time. You can't force people to give you their data because participants have rights and people have rights. So it's at least very, very difficult, which is why we don't usually do it, right? We usually take samples that represent the bigger population. So, coming back to some terminology we talked about last time, we talked about empirical versus simulation, right? And so what did we say was the difference, anyone remember, between empirical versus simulated?
Empirical was just the theory and simulated was something that you proved.
Kind of reversed, right? So empirical, and I just did a Google search so you can see like the actual terminology. Empirical means based on, concerned with, or verifiable by observation or experience rather than theory or pure logic, right? So empirical data is the real data you collect. When we had people actually vote, the guy on the left or the guy on the right, that was our empirical real data, versus when we flipped a coin to represent that process, that was a simulation.
Wait, so what is simulation? Is that how you get the real data? Simulation?
No, so simulation it's like a hypothetical version of collecting data, right? So just if you think empirical, some synonyms it has are real, firsthand, actual. That's the actual real data you collect.
After the simulation?
Separate. Yeah, and so empirical is your real data. I actually had you vote left or right. That was empirical because you really voted, right? I didn't tell you what was the point of it. I said choose a face, left or right, and I actually collected that data. That's the real data, right? So empirical means like the real thing. So empirical data is data we've actually really collected somehow. It's like real study data. Because empirical just means it's verifiable by observation. So if you're observing this actual data, that's our empirical data. Versus simulated data is not real data. It's imitation data. It's a way of sort of imitating what could happen. It's more like a model of what could happen.
That was the penny toss.
So where you really voted on the faces left or right, that was our empirical data. But then when I had everybody flip a penny to sort of simulate what if you chose based on random, that was the simulation. It wasn't you really voting, it was simulating what could it look like if this is how people voted. Are we making sense? Right, so to do the simulation, we need some sort of model to base our simulation off of, right? So when we decided to do flipping the coin, the reasoning behind that is because that's what it could look like if you're choosing at random, right? Because flipping a coin gives you 1 out of 2, and if people are choosing at random 1 out of 2 options, that's sort of our model that we base that simulation off of. So these things are going to sort of tie together population and sample, empirical and simulation. All these pieces come together in our null hypothesis testing. They all play a different role. And so knowing what each of these things is on its own is going to help you see the bigger picture of when they come together. So review this term sampling distribution. How do we get that? What is that? Anyone remember? So we said we have a big population and we can pull a sample and we can calculate some statistic like a mean.
Oh, new
Right.
sub-export?
And so I could do this over and over and over again, right? Just take lots of different samples. And each time I'm calculating some statistic like a mean. Right? And so then if I take each of these means that I calculated and I plot those, right? So I make a new distribution. These are all sample means. And so that one came in down here, that one was over in the middle, that one came over here, this one all was sort of close up here, right? I could start doing this where I just take sample, what's the mean, and then put it on my graph. Take another sample, calculate the statistic, put it on the graph. Take a sample, plot this, right? Do the statistic, put it on the graph. This is how you make a sampling distribution. Right? So the population has some distribution to it. It might look like this. It might look like this, right? We don't know what it really looks like. But every person in that population has some data. And theoretically, we could plot all that data out and get some distribution, right, for the whole population. We don't know what it looks like, though. It's a mystery. We're trying to figure out what is going on in the population. So to get that window to the truth, right, this is the truth, we want the window to the truth, we pull some data, and then we can figure out what's the distribution of this guy, and what's the mean of him. Okay, but then, do we know if this mean is the same as this mean? Not really. We could think it might be close, but we don't know how close it is. Okay, so do it again. Pull a different sample, and we get a new distribution, and this means a little bit different. So how do we know which of these means is the mean?
You gotta do it a bunch of times, and then you gotta get the mean of the mean.
Right, we could get this one, and maybe this one's a little bit different, and it's somewhere in between. How do we know what the mean of here is, right? So each time we get a little bit of a little window into this truth, and if we do it enough times, we can sort of figure out what do we get? Maybe we start to see some numbers pop up more often than other numbers, right? So if all of these are sort of hovering around 5, then maybe that's because the real mean here is 5. Once in a while we get a 2 or a 7, but most of the time they stick around that 4 to 6 range, right? So we could get each of these, like I said, each time we're keeping track of our means, and we'll notice that some numbers start to occur more often than other numbers. Okay? And so then eventually, if we do this enough, we should start to be able to see a shape take, like form, from all of these little means that we're taking.
Okay, so I understand what this is,
Mm-hmm.
but I don't understand how that could really represent a population, because like with the coin flip, it was one thing, right? It was like flipping a coin, and what we did when we flipped the coin was all we could do was rule out that it wasn't random. So with this, we couldn't simulate all of this data and expect to get something.
If we don't know what this is, right? We can't simulate what we don't know.
Yeah.
That's the big problem here. That's why this is so confusing,
Okay.
right? So you are perfectly on the right track here. So we have a null hypothesis and an alternative, and they sum up everything that could. Either it's at random or it's not at random. It has to be one of those. We don't know what the actual case is, right? And so if it's not at random, what is it? We don't know, right? We can't build a model on something we don't know. Is it that 30% would choose the guy on the left, or 80%, or 75%, or 25%? We don't know what that is. That's sort of the mystery. We can figure out what this would be. Like we said, if people are choosing at random between 2, we would expect 50% to choose one way.
Yeah.
Right? So this is the one we know. And this is what we therefore base our model off of. Because you can't model something you don't know. So we would love to know, okay, we get a sample of data. We would love to know how likely, if I got this sample and I got this result, like in our case, we got 60%, we would love to know how likely is it that this is true. Because we don't know what this is, we can't do that. We can't go that direct route. That would be the best thing for us if we could say, oh, this is so likely to happen or not happen. This is what we really think is happening. We can't do that because we don't know what to base the model on. We have to do instead, okay, well, we know what this looks like, so we can build a model on this, and then we can say, how likely is this thing that we don't really think is happening? We say, how likely is this thing to happen? And if it is likely, then we just got to stick with this. If it's not likely, then we can sort of assume it's the other thing, right? So it's this very roundabout process.
Yeah, and see, so it's not proving what you know, it's proving that it's not that.
Yeah, so we start with,
it's not saying anything except for it's not this.
right, we're not testing the alternative hypothesis, we're testing the null hypothesis. We're testing how likely is it if nothing's happening. And if it's not likely, then we can say, well, then it's probably not this, it's this. This is what intuitively what we want to be able to do, but because of the way the real world works, we can't go straight from here to here. We have to do this roundabout process.
So we're saying we know it's not nothing, so it has to be something.
So it has to be something, right? It's very unlikely that it's nothing. Yeah.
So this is is it weird?
Yes. How weird is it if this is true?
So then if it is unlikely, if it's that, and we go to the alternative hypothesis, that's where we would say, okay, now what variables can we use to say, is it this, or this? Is that how we end up getting actual graphs? Because somebody deemed that there is a relationship.
I mean, the graphs would be based really more on your sample. And then this process, this is the null hypothesis testing. This is ultimately you make the decision, do we have to stick with this one because it's still kind of likely? Or is it so unlikely that we reject it and go here? And so we've talked really about relationships so far. We're gonna sort of shift at this point and start talking about differences. But I think in the next couple classes, you'll start to see this is sort of like the groundwork of what it is we're doing. So we start out by making, right, this is what we would like to know, but what we really are doing, right, so we're gonna end up with this, what we call like a distribution triad, which just means we're talking about 3 different distributions. We have some mystery population, right, which represents the real population. And we have some distribution that belongs to this real population, real people. But we don't know what's going on there. We can take a sample, but again, we don't know how likely it is that this matches this, right? It could, because it's happening at random, it could be way off. We don't know. So what we do instead is we say, okay, well, we don't know what this population looks like, but we know what a population where the null hypothesis is happening looks like, right? If this was actually the case, we would know that 50% chooses the guy on the left. So when we build our sampling distribution, we're not really building it from this population. We're building it on this theoretical population where the null hypothesis is true. So we build this, okay, then it should be around 50%. And then we can compare this to this theoretical one and determine how likely is it, and that's what's gonna make us, because we're ultimately trying to decide about this unknown one. Could it have happened like this? If so, then we just assume that the null hypothesis is true. If it looks like it is so unlikely to have happened, if this is true, then we say that's not true, it must be something different.
You know how you're saying take a bunch of samples and get the mean for it? Is there a set number of times that we're supposed to do that before we can get a accurate sampling distribution?
So the thing is, when we're making these sampling distributions, we're not really making them this way, like I first drew. That's the concept. How we really make them, we use the shortcut that she talks about in the video.
So that's CLP.
The central limit theorem. So because we're really making them based on a hypothetical situation, if the null hypothesis is true, we can jump using the central limit theorem straight to here. It's not like we don't really do sample tens of thousands of times. We would never get anywhere if we tried to construct it that way. So what we do is we say, well, what would it look like if the null hypothesis is true? Build it based on that, and then we use that comparison to tell us about this one. So really we have like we have like reality and what might be reality.
And we're assuming 50%?
Yeah, in this case it would be 50% if they're choosing between 2 at random.
What if the null hypothesis has been rejected, then what do you do?
Then that's at the end. That's what you would say. We don't think that's actually the case, we think this is the
Then you
case.
don't have to use the
That's your
central limit
evidence.
theorem or any of that?
But you're using that earlier to get to that point where you reject. You can't reject until you get to that point.
Are we gonna go over central limit theorem? That's so hard.
Yeah, a little bit. So how do we theoretically get a sampling distribution? What it represents is if you took tens of thousands of samples from some population and you plotted some statistic, right? That's what it represents. In practice, we don't really do that. We use the central limit theorem to get there. And we can do that because, this is one of the answers, one of the questions, because they've proven it mathematically that they always follow the same pattern. Like there are things that hold true mathematically about sampling distributions that are based on varied population distributions. Right, so we'll kind of get to that, but this whole how can we use sampling distributions, this is how we're going to use it, right? This is why we're spending so much time talking about it, is because it's the underlying principle to the statistics that we're gonna do, like to the actual tests we do to make our decision one way or the other, is this is what's happening. Is we're creating some like hypothetical model sampling distribution that we can compare our real empirical sample to decide likely or unlikely, and then just make this decision. Which one is it? So this is like all these little individual pieces all fit into this big cycle that we do. So we take our result from our real empirical sample that comes from this unknown population, and we compare it to the sampling distribution based on our hypothetical null hypothesis population. And we ask, how likely are we to get that here? If it's likely, or in other words, how weird is it to get this here, right? If we find that it only occurs like way out here or way down here, that would be super weird, because where's most of the data here? Where it's stacked up in the middle. If it's out here at the end, that means it doesn't occur very often. It's super rare. Right? So if it's super weird and super rare, then we can say it's probably not this. It's probably the alternative. Right? So this is how we're going to be using it. So when we're talking about models, the model in this case is really a model of what's happening and if the null hypothesis is true. And again, the model is just like an approximation or a simplification of what's happening sort of in the bigger picture. Again, models, because I have in there, like, what's the difference between model and a hypothesis? They're related. Models are about relationships between variables. Hypotheses are also about relationships between variables. Right? Models are simple, but the real world is messy and complicated. So when we use a model, we don't expect it to be right every time, but we expect it to be close if it's a good one. We talked about hypotheses, and namely these two big ones that we talked about, right? So in statistical testing, we're really testing the null. We're testing how likely is it if the null is true, not how likely is it if the alternative is true.
So is this number 5? This would be called model testing or null hypothesis.
So why is it called model testing or null hypothesis testing? Because we're actually testing the null hypothesis, not the alternative. Even though the alternative is sort of what we're interested in, since it's a mystery, we don't know what it looks like, we have to go with we have to test what we know, which would be the null, that there is no effect or no difference or no relationship. Because at least we know what this one looks like.
So this is basically the method for, is it weird?
Mm-hmm. Yeah. So we're not saying, is it weird this way?
Right.
Against the one we really care about, because we don't know if it's weird or not, because we don't know what to compare to. We can say, is it weird here, because we know what we can compare against.
Based on what we're thinking.
Yeah, so it's this roundabout method, and that's why this is very confusing.
It's just weird. It's
a weird way to think
because
about
we're
it.
making something up. We're kind of saying, oh,
Yeah.
well, maybe it looks like this.
Yeah.
Okay.
It feels,
Fake.
yeah.
Okay.
Right. Okay, so again, just to reiterate, the null hypothesis is always no effect, no difference, no relationship, random chance, nothing's happening. Not the one we actually care about, but it's the one that we know what it looks like. The alternative is not that. There is a relationship, there is a difference, there is some effect, but again, it's a mystery what that is. So that's why we have to compare here, because at least we know what this looks like. This is what this is saying too. It would be nice to be able to know the probability of this being true, given our sample. That's not possible, it's not the way the world works. We have to instead determine how likely is it that we would get this if this is true. This is the logic behind null hypothesis testing. And then after we see how likely was this, we can make a decision. Okay, if it's fairly likely, then stay here. If it's not likely, reject and go here. All right, so, that's I told you it wasn't gonna be fast, but to try to summarize some of these big concepts, right, and pull them together. Where does sampling distribution fit in? Where does sample and population and empirical versus simulated? All these play like a part in this big null hypothesis dance that we do. So number 5, why is it called null hypothesis testing?
Because we're testing.
Because this is the one we're testing. We're actually testing that, even though we would love to test the other. So thinking back, number 6, thinking back to when we actually originally collected that data, I had you answer 3 questions, right? So the first question was, how much does the guy on the left look like Tim? Give him a rating on a scale from 1 to 6. How much does the guy on the right look like Tim? Give him a rating on the scale 1 to 6. And then the third question was, which one's Tim? So thinking about those 3 different questions I asked, I want you to think about which ones are continuous and which are categorical.
The first 2 are continuous, and the one's categorical.
Yes. So when I asked you, rate on this scale of numbers from 1 to 6, that's continuous. Versus when I asked, pick one, that was the categorical one. So A and B, the left rating and the right rating are both continuous. C, pick Tim, that's categorical because you either picked this group or this group. That's pretty clear? Okay. So, number 7 says, on the next page is a histogram of the left ratings from class. So I'm talking about this graph here. What kind of distribution is this graph of? Is it a population distribution, a sample distribution, or a sampling distribution?
Sample distribution.
I hear sample, did I hear anything different? Why is it not a population distribution?
We don't make distributions of population.
I think theoretically we could, but do we have data for every single person we care about?
No.
I care about you guys. But in this example, I don't only care about you. I don't only care about whether my classes have facial prototypes. I care about people in general, right? So it's not all the people in general. It's only specifically my sample of data.
And it's not the mean of everything, so it's not.
Right, and it's not the sampling because I didn't do the sample over and over and over and over again and then plot that, right? It's just one sample of data. So in this scenario, this is what I'm talking about. This is what the graph represents. It represents my sample that came from a bigger mystery population, right? So we know here we got 60%, or in the other example, 60%. In this case, we're not talking about percents anymore.
What if anyone says, should we use a proportion to summarize this rating?
So this is sort of part B. So when we were talking about who did you choose, how many chose left versus right, that's where we used a certain like percent, 60% chose the left. Would that make sense to summarize this data? If I gave you a proportion to summarize what's happening here.
Yeah, you can do that.
You could, but the thing is, with proportions, they're really better if you have just 2 options, right? Or if you're talking about categories. Here we're really talking about on a range of numbers. So when you're talking about a range of numbers, how do we generally summarize a histogram like this? Shape, center, spread, right? Because this is continuous data now. It's not categorical, this or that.
So no, because it's a range of numbers, we would want to use the shape, center, spread?
Yes. Right, it's no longer a this or that. Now it's a, what was the average? How spread out is it?
What would be an example of that? Like,
How many chose left versus right?
that's what we're talking about.
So here, this is only rate the guy on the left.
From
1 to a 6. Rate the guy on the left.
Oh.
So this is like new data.
I thought we were talking about just left and right.
Yeah,
So I said,
there you
that
go.
would make sense to use proportion.
So this one is rate the guy on the left from 1, doesn't look like Tim, to 6, that guy's name is Tim.
Okay.
So C, shape, This histogram came out kind of weird because PSPP doesn't let me mess with the scaling. So the numbers at the bottom, imagine there's no gap there.
Okay,
There really
was this a binomial?
There really shouldn't be a gap there. It's the way that PSPP did the numbers. You see at the bottom it has half values, and I couldn't change it. So imagine there's no gap. You have to summarize this shape, unimodal.
Like that.
Yeah, right. It looks like it's got a hump in the middle. Maybe a little taller on the right side, but yeah, it's not too far off from unimodal, sort of symmetrical, right? Where's the center?
3.9.
So the center, remember when we're talking about something like this, the center is the mean, and we can see the mean on the left there is listed 3.9. And the spread gets cut off, but spread we would represent using the standard deviation, right? That tells us approximately how spread out the data are on average, and in this case, it's about 1.4. So that's C if you didn't get that. All right, so the shape, it's roughly unimodal, not quite normal, but it's sort of.
So
The center is 3.9, yeah, and the spread is about 1.4. So given how many people chose the guy on the left, 60%, are these ratings surprising to you at all? Or is this sort of what you would expect?
Wait, what?
So keep in mind, this is the guy on the left. How much does he look like Tim? And we can see, on average, people voted about 3.5, or 3.9. Right, so somewhere between 3 and 4, around 4.
That makes sense because we got 60%.
And we got 60% chose the guy on the left.
That makes sense.
Does that seem like it
3.9
corresponds
is
with what we saw?
Yeah, 3.9 is about 60% if you're going from 1 to 6.
Does this look like it sort of supports the facial prototype idea?
Oh, wait.
Yeah, right? It's
So, no, we're not really surprised?
it may vary.
Okay.
Maybe we would expect more people to rate higher on the higher end, but yeah, 60% again is not that high, so maybe it's not really surprising.
No, I'm not really surprised.
So number 8 says, do we have to simulate a sampling distribution of means, the SDOM, like we simulated the sampling distribution of proportions using the pennies? Do we have to do that? Or is there another way? What is it called?
Oh, central limit.
This is where central limit theorem comes in, right? Because we could hypothetically say, what would this distribution look like if the null hypothesis is true? And then simulate that over and over and over and over and over and over and over again to create a sampling distribution. Thanks to the central limit theorem, we're going to jump straight to the sampling. We can jump straight to the sampling distribution. All right, so central limit theorem is really just going to cut out that middle step. And we can do that because mathematicians, smart people, statisticians, whoever, figured out it works every time. So if it works every time, we don't have to recreate it every time. We can just use the characteristics they came up with and apply them.
So Nina says, why are we allowed to do this? Just because it's proven we can?
Yeah. So why can we do this? Because sampling distributions, they're predictable. They always follow the same pattern. And that's true because they found mathematically the proof works out. Where do I draw?
So you're gonna go over how we do the central limit theorem? How that, what we do to do it?
So the central limit theorem is really, it's just like a tool to say we went from here to here.
Right, but how do we show that?
We can,
We just put, how do we actually get, I don't understand.
so we'll have some population, hypothetical population, and we'll get to the point where we can just draw the sampling distribution of what it would look like. We're not gonna do that today.
Eventually, is there a formula?
There is a formula to help us get from one to the other, yes.
What is?
And so it'll be we'll say if we have a population that looks like this, we'll know that the sampling distribution the mean is gonna be the same.
All the
Right.
times?
Yeah. That the mean is always gonna be the same as this one, and we'll have a formula for if the standard deviation is something here, we can figure out it's always gonna be the same thing here.
Yeah, okay, so that's just talked about in the notes.
Yeah. And
And
so we'll
that's
get
the
to this
central limit
point.
theorem right there?
Right, so in between these two, how we get from this to this, that's the central limit theorem. That lets us just jump from one to the other.
Wait, the top one is the population?
This would be the population, this would be the sampling.
Then what do you mean to get from the population to the sample? Why did you
Sampling.
Oh.
So we can have, like here, we have a hypothetical population, but what we need is this, so that we can compare our sample here.
Oh, the hypothetical
So
population.
the central limit theorem is what's gonna let us jump from this hypothetical population to the sampling
Which
distribution.
is then gonna go to the regular population.
Which then we compare and make our decision about this guy.
So
Yeah.
try it.
We've got lots of different pieces. Yeah, we'll come back to this. So the central limit theorem really is just what's gonna let us jump from here to there. We don't have to actually get the simulation every single time. So, okay, so that's why we're allowed to do it. So let's say that we wanted to create a model based on random chance for this rating idea, right? So we had people rate from 1 to 6. So if we were to create a model based on random chance, what might that look like? What percentage of people or how many people would we expect to choose each of the options?
The 50-50.
So we have 6 options now, right?
So now
1,
we're
2, 3,
still
4,
not at
5,
the
6.
left or right. We're still on the continuous data, right?
Right, so this rating, if people are rating at random, what might that look like? Will we expect more people to choose one particular number versus the others if they're choosing at random?
No.
Would we expect all the numbers to be about the same?
About. I would
So,
say about because it'd be random, right? We would expect each
Right.
number to have an equal chance of being chosen.
right, yes. So you can think of this one sort of as like if you had a dice,
Yeah.
right, with 6 sides, and you rolled the
You
dice
have an equal chance.
or die,
All
I forget,
around.
right?
One die.
You could get a 1, you could get a 2, you could get a 3, 4, 5, or 6. And if people are just each rolling 1 die, then we would expect these numbers to be fairly equally represented. Right? We wouldn't expect more people to get a 3 than anything else. That's not really how those work.
So
Right.
like
So then what would the
15,
shape of the
16%?
distribution be if it was, oh, that's where she said,
Yeah.
what's it called?
So we would expect, if they're really choosing at random,
1 out of 6 each time.
there's like a 1 out of 6 chance of getting any of these. And so we would expect them to come out fairly even. So this general shape would be, I don't remember, we actually said it's called uniform.
Uniform.
Mhm. Versus what did we really see in our sample?
Uniform.
Not uniform.
It wasn't uniform,
Yeah.
right?
So the center of the distribution would be 3.5?
It would, yeah, it would be if you calculate the mean of 1, 2, 3, 4, 5, 6, we would get the mean, and I did a really bad job drawing this, right? But it would come in like 3.5.
That would be the center. of the
That would be the
distribution.
center, is what we would expect.
And the spread is 3.
The spread would be whatever the average of, whatever the standard deviation is, I don't know what it is off the top of my head.
And when the standard deviation is go to 6 and 1?
So remember, the standard
Uniform?
deviation is, you're thinking of the range. The standard deviation is if we balanced out how far 3 is from 3.5 and 2 is from 2.5.
Right, but if it's uniform, then it's equal, then it would be 3 on that.
It would
case.
work out somewhere like,
Oh.
probably like that. Because we're averaging the ones that are close and the ones that are far. So it wouldn't be, because not all of them are really far away. Some of them are closer, so it'll be somewhere in between.
So
So
the
from
spread-
1 to 3, from 2 to 3.
It would probably be something, I don't know, 1.5-ish.
So do we put that for the spread?
Yeah. Whatever the standard deviation of 1, 2, 3, 4, 5, 6 is, that's what we would expect. Because 3 is close to 3.5, but 1 is far away from 3.
Yeah.
So it would end up somewhere in
So you'd
between.
average out those differences
Yeah.
for each thing. Okay.
Mhm.
The center, we have 3.5, that's just like the median. That's
That-
literally
it would be
the
the
mean.
mean.
The mean.
Yeah, if we added 1 plus
It's
2
a
is
median.
3,
I mean
plus 3
median.
is 6, that would be 10, 15, 21, divided by 1, 2, 3, 4, 5, 6. Does that work out? 21 divided by, I think so. Right. Yeah, does that work out? Okay, so, yeah, so it's just mean and standard deviation, right? So this would be our hypothetical, if the null hypothesis is true and people were just picking a rating at random. This is what we would expect it to sort of look like. From this, we would be able to build a sampling distribution that we could then compare our real sample, which had a 3.9. We could say, where does this fit in, and is it weird or not? And that would allow us to make a decision of, then do we think this is what's happening in the real population or not? So this model that we drew here, does this represent a population or a sample?
This would represent the
This represents what's happening in the whole population.
I thought we didn't make models about the population.
But
We
it's a
always
phase.
make models about population.
But it's not the real population, right?
No, it's a hypothetical, it's a simulation.
Which is
right?
why we're able to just say, this is what we think it looks like.
Yes.
Because if we were not in this concept and we were doing something from like 2 weeks ago, we wouldn't be drawing out our population.
Right.
Okay.
So, and then
Hypothetical.
what gets us from this hypothetical population down to our sampling distribution, that's gonna be our, thanks to the central limit theorem, we can just jump to this point.
So for randomness, we're kind of flipping it. We're kind of doing things backwards. We're thinking about our population to try to get our sampling distribution. So that way we can consider the real population.
So we think we have sort of like two hypothetical populations. Like we have a real population, but we don't know about it. And we've got this hypothetical one that we use to build a model. And from that model, we get a sampling distribution that we can compare our real sample to make a decision about the real population. Yeah. It's this very circular reasoning kind of, like, which is why it's hard.
So the more pieces, the more sense.
Yeah. So, so in this situation, what would if this is the hypothetical model of the population, what's our sample? This would be our sample, right? Our real data where people actually voted, the 1, 2, 3, 4, 5, or 6. This is really our sample.
So we just put the histogram.
Yeah, the people who really voted.
So our empirical data.
Yes.
So our sample could not be our simulated data.
Right, our sample is not simulated. Our sample is real data.
So it says, how will we create a sampling distribution by using the CTL?
Mm-hmm. So how would we get from this hypothetical model population to our sampling distribution? The central limit theorem will give us the tools we need to know what this is going to look like. So that we'll be able to compare this to make a judgment about this. So then I've got like 2 more slides that'll sort of really just sum up this concept that we've talked about, and then we'll get into doing the lab portion where you're playing with the CLT simulator on the computer. Okay. So 10E says, think about when we compared our empirical sample of data from voting left or right to the sampling distribution to say how likely we thought our result was. Okay. So what did we do to review? First, we simulated a possible outcome based on the model of random chance. That's where everybody flipped a coin, right? We simulated what does that look like, and then we calculated the proportion based on everybody's coin flipped.
So this is the answer for number E?
Yeah, this is like big picture kind of sum up. Right, so we're all clear on that. We did a simulation, and we calculated the proportion that went with that. Then we, like if you think back to the computer, what it was doing is it flips the coins and then it plots the proportion or the number of heads. Right, so first we built our sampling distribution, then we told the computer, do this 10,000 times. And it did it 10,000 times, and each time it flipped 45 coins at random, calculated the proportion, and dropped it onto the plot. Until eventually we had this nice stack of proportions. Right, to create our sampling distribution. All with me so far?
So our sampling distribution is our simulated data.
Yes. Then we could take our real proportion that we got, which was 60%, and we compared it. We wanted to say, okay, then how likely is this 60% based on our sampling distribution? And we found it was 11 to 12%. And then from there, we can determine is that likely or unlikely. And E and F are really just the same thing. F is just an opportunity to, once you think you've absorbed this concept, try to retell it in your own words. Let's do the right. All right, so step one, come up with your model of randomness. Pull a bunch of hypothetical sample. Figure out your statistic and plot it, and do it lots and lots and lots of times. That gives us a sampling distribution based on our randomness model. Then we can take our real result that we got from our sample and say, where does this fit in? Is it likely or unlikely? If it's likely, we don't reject the null. If it's unlikely, we'll reject. Go with the alternate. Right? So the sampling distribution is what we need in order to compare to make a decision. So then we determine from that, okay, our real results, do these occur often or rarely in our simulated one? Okay. So if we simulated one that looks like this, where are the ones that occur often?
Right in the middle. Biggest one.
Right? If it's stacked up high, that means there's a lot of that number. Where are the ones that occur very seldomly or rarely? On the tails. Right? Out here, that means we only had a couple of times out of our thousands and thousands that ended up in these areas. Right? So this will help with one of the questions for today's, like in the simulation. Ones that occur often or are likely to happen in the middle. Ones that are rare and unlikely are in the tails. So we could say, where does our result fit in? If it's in here, then if it occurs often, then it's not weird. It could be the null hypothesis then. Right? Not weird, don't reject it. If it occurs rarely, out in one of these little tails, that's weird, because it doesn't happen very often. And so if it's weird, then we think maybe it doesn't really come from this. Okay, so if it's often, then our empirical sample result could have occurred in a population where people just choose at random. If it's weird, then it's unlikely to occur in a population that chooses at random. So we would say then it's more likely that it's not random, it's more likely it's the alternative. So we're using this, how often does it occur? Is it weird, not weird? To make our judgment of, is it possible based on our null hypothesis, in which case we just keep it? Or is it super weird and we think it's not the null hypothesis, we go with the alternative. Reject that, go with the other. And so this is the whole like circle concept. So, like I said, I hope it recorded all of that. So if you have trouble sleeping at night and you want to